Hello, my friends. Today we're going to take a look at 8.1, which is exponential transformations and key attributes. An exponential function is a function that has a variable as the exponent. Take, for example, the one that you guys probably worked with in Algebra 1, y equals 2 to the x power. We have the graph of y equals 2 to the x power over here. You can see that if you plug in a number, 0, 2 to the 0 power is equal to 1. 2 to the first power is 2. And 2 to the second power is 4. We label what's called the critical point, not to be confused with the critical point that you will see later in calculus, as the y-intercept, because it has a distance of 1 from the horizontal asymptote and helps you determine the base. With the parent functions, that's going to be the point 0, 1. The horizontal asymptote is at y equals 0. That is because if you start plugging in negative numbers as you move towards infinity, so for example, 2 to the negative first power is 1 over 2, 2 to the negative second power is 1 over 4, and then 2 to the negative third is 1 over 8, and so on. The fraction keeps getting smaller and smaller and smaller, and it gets very, very close to 0, but never quite touches 0. So we have it leveling off towards y equals 0 at negative infinity. The domain for exponential functions is all real numbers. And then the range are going to be the numbers that are greater than 0, so from 0 to infinity. It's bounded by that horizontal asymptote. This function, y equals 2 to the x, is an increasing function. As the x's get bigger, the y's also get bigger. And it's increasing across its entire domain. It doesn't change directions. And this is an example of exponential growth. You can tell it's growth because as the x values are getting bigger, the y values are also getting bigger. So, growth. Okay, well, what happens if you have a reflection over the y-axis or the exponent is negative? 2 to the negative x power, well, that's equivalent to 1 over 2 to the x, which can be written as 1/2 to the x power. If we were to sketch a graph of this over here, and make a little table, I'll go ahead and plug in a few points. So if I plug in negative 2 into this function, that becomes 4. So we have the point negative 2, positive 4. If I plug in negative 1, I get 2. If I plug in 0, I get 1. And then if I plug in 1, I get 1/2. And my function is just reflected across the y-axis. The critical point is still that vertical distance of 1 away from the horizontal asymptote. So it's 0, 1 in this case as well. The horizontal asymptote hasn't been shifted up or down, so it's still at y equals 0. The domain is all real numbers, and the range are the values that are strictly greater than 0. But instead of increasing, this function is now decreasing. As our x values increase, the y values decrease. And this is an example of what we call exponential decay. All right, let's practice finding some key attributes of these functions. Y-intercept, to calculate that algebraically, we're going to plug in 0 for x. 0 plus 5 is 5. 2 to the 5th minus 3, that gives me 32 minus 3, which is 29. So we have a y-intercept at the point 0, 29. For the x-intercept, we plug in 0 for y. We get 2 to the x plus 5 minus 3. We do run into an issue here, though. We don't have the tools in our toolbox to be able to solve. We can add 3, and we get 2 to the x plus 5. But at this point, we need something called a logarithm, which will help us solve for the exponent. So instead of using logarithms, at this time, I'm going to show you guys how you can do this in your calculator. So in your calculator, you guys will have a TI-84, but I have this emulator here. We have 2 to the power of x, and then plus 5, and then minus 3. Okay, you'll graph your function. You've got that right there. Okay, now you're going to use the trace function, or the calculation function, by pressing the second, which is the blue button, trace. And then option number 2, you're going to calculate the 0. You do have to bound this, so you're going to use your left and right arrow keys to pick a point that is to the left of where the x-intercept is. And you want to get pretty close. And then you're going to pick a point that's to the right by scrolling right. You're going to press enter. And then you calculate. So we have an x-intercept at approximately negative 3.415. And I round to 3 decimal places. So negative 3.415. So we write that as a point. Okay, the maximum and minimum of the exponential function on the interval from negative 4 to 3. We have the same function here. This is an exponential growth function. Okay, and I'm looking from negative 4 to positive 3. Since this is exponential growth, this is increasing over time. So we should have a minimum at x equals negative 4. If we plug negative 4 into our function, we get 2 to the negative 4 plus 5 minus 3, which becomes 2 to the first power minus 3, or negative 1. We should have a maximum at 3. We get 2 to the 3 plus 5 minus 3, which is 2 to the 8th power minus 3. All right, 2 to the 8th power, I may not know what that is off the top of my head, but I sure can do the math. Here, I know I can split this up as 2 to the 5th times 2 to the 3rd. 2 to the 5th is 32, and 32 times 8 gives me 256 minus 3. Let's go ahead and double check my math because I'm on the spot. So I want to make sure that I don't make a dumb mistake. Here we go, 2 to the 8th, and it's a miracle. I did it right. Woo! Okay, so we have a maximum at 253 and a minimum at negative 1. Okay, let's practice. So on your test, you guys are going to have a calculator for finding the key attributes, but you won't have it for graphing. So we're going to practice graphing using only transformations, and then we can find the intercepts using our technology. Okay, here we have negative 4 to the x minus 5 plus 2. For any exponential function, the parent function is just whatever the base of that is. So here, the parent function is the base raised to the x power. So this would be 4 to the x. That base does not affect the transformations. All right, that is just the base of the exponential. The transformations happen outside of that. So first transformation we have is a reflection over the x-axis for that negative. Then minus 5 tells me this graph is being shifted to the right 5. And then the plus 2 means it's been a vertical translation up 2. Again, that 4 does not affect the transformations. That is the base of the exponent. Okay, now I'm going to graph this before I find the intercepts. So I'm going to use the parent function 4 to the x to graph. All right, if I plug in 0, 1, and 2, 4 to the 0 power is 1, 4 to the first power is 4, and 4 squared is 16. Now I'm going to apply those transformations. I have a reflection over x, and I'm going right 5. So I'm going to, for the x values, I'm going to add 5. And then for the y values, they get multiplied by -1, and then I add 2. All right, adding 5, we get our new points to be 5, 6, and 7. And then we have -1 plus 2 becomes 1. -4 plus 2 becomes -2. And -16 plus 2 becomes -14. Plotting these on the graph, we have 5, 1, 6, -2, and 7, -14. Okay. Now you'll notice the difference between this one and this one here is I don't have a clear picture of what's happening above these 3 points. So let's think through this. If we normally have a horizontal asymptote on the parent functions at y equals 0, if we are shifting up 2, that is going to shift the vertical asymptote also up, the horizontal asymptote up 2. So we have a horizontal asymptote at y equals 2, and the function is going to level off towards that horizontal asymptote. The domain of all exponential functions is all real numbers, and the range is determined by that horizontal asymptote. I can see that on this curve, it's going to be all of the y values that are less than 2. Okay, let's find the intercepts of this function. Again, we're going to go into our calculator. I'm going to clear out my function. I've got negative, and we want to type it in exactly how we see, 4 to the x minus 5 plus 2. We're going to graph that. Okay. To calculate this, again, we do second trace. And we're going to calculate the 0. We gotta scroll over. Unfortunately, I can't just hold the button down on the iPad. So here I'm scrolling. Enter. Enter. We got a right bound. Oops. And we have a 0 at 5.5. Okay, so our x-intercept is at the value 5.5, 0. You can also calculate the y-intercept using your calculator. If you do second trace, you scroll through the options, you'll see that it's not a specific option, but you can do value. So you do where x equals 0, and it'll tell you what the y value is, 1.99002. And it's the same thing on the TI-84. So I'm going to round that to 3 decimal places. I get approximately 1.99. And let's see, what was the third decimal place? 1.999. Exciting. Okay, you can also calculate the y-intercept algebraically at this point. You literally just plug in the 0 for x. If you plug in 0 for x, you get -1 over 4 to the 5th power plus 2. -1 over 4 to the 5th is really close to 0, so I recommend using your calculator for that one. Okay, finding the minimum and the maximum on the closed interval from -3 to 7. We can see that this function is decreasing. And we are restricting our view of it only from -3 to +7. Okay, there's no vertical asymptote here, so both the min and the max do exist. We should have a maximum at the x value of -3, so we're going to plug that into our function. And we get -4 to the -8 plus 2. And then for the minimum, we should have that at x equals 7. Oops. Okay, we've already actually calculated the value at 7. We should get -14. Keep adding numbers in here. +2, not +12. All right, we get -16 plus 2, which is -14. And then we can plug this other one into our calculator and see what we get. So here we should get something that's pretty close to 2, but not quite 2. So we have negative, oops, let me quit out of this, -4 to the -8 plus 2. We get 1.999. Very close to 2, but not quite 2. Okay. Let's go ahead and take a look at something where we have a base that is a fraction. So we have -3 times 1/4 to the x plus 4 plus 3. There are a few ways that you can approach this. You can use the parent function as 1/4 to the x power, or you can use the base of 4 to the x and state that there's a reflection over the y-axis. I personally am a fan of using whole numbers when possible because I don't get confused, but I know students get confused. So I'm going to rewrite this with a base that is a whole number. I have -3, 4 to the -1, x plus 4, and then plus 3. These two are equivalent. This is just using a whole number base. So the transformations that we have using this as a whole number base, we have a reflection over the x-axis for that negative in front. Since there is a number being multiplied on the outside of the base, there's a vertical dilation by 3. There is a reflection over the y-axis for that negative, and then it is going left 4 and up 3. Again, you're not going to have a calculator to graph, so let's practice graphing using the transformations. I'm going to use the parent function 4 to the x, and I'm going to plug in 3 numbers. You can use 0, 1, and 2, or -1, 1, and 2. I personally prefer to use whole numbers. So here I get 1, 4, and 16. Applying the transformations to the y values, this is going to be -3y plus 3. And then to the x values, we should get -x minus 4. Okay, multiplying, we get -4, -5, and -6. For the y values, -3 plus 3 is 0. -12 plus 3 is -9. And then we get -45. So it decreases pretty fast. And again, this graph has been shifted up 3. So comparing it to the parent function, when we plot it, our horizontal asymptote has also been shifted up 3 to y equals 3. So we have that to bound our function. Okay, we have -4, 0, -5, -9 is right here. And then -6, -45, you don't have to plot. It's not going to fit on there. But it just tells you the direction that the graph is going. So it's going to continue increasing down. Let me see if I can actually draw it on my iPad. As it moves to the right, it's going to increase towards the asymptote. And there's my function, more or less. Okay, domain is all real numbers all the time. We have -infinity to +infinity. And then I can see that these values are all of the y values less than 3. All right, let's find our intercepts. Well, we don't have to use the calculator function to find the x-intercept. That was actually solved for us. We have -4, 0 for the x-intercept. And then for the y-intercept, I am going to use the calculator for that one. So we're going to go into y equals. I'm going to clear out my function. I've got -3, and you can type in either the transformed function with the new base, or you can type in the original function with the fractional base. Either one's okay. And then we got +3. Okay, we graph it, bam. Calculating our x equals 0. I've already done that in this function, but again, you'd press second calculate value, and then you would go 0. And we would have one at 2.988. All right, finding the maximum and the minimum from -5 to +2. We're zooming in on our function from those values. I can see that this function is increasing. Oops, I did it way too far, sorry. It should be -5 to -2. This function is increasing over time. So I should have a minimum at the x value of -5 and a maximum at -2. Okay, again, we're going to plug these values into our function. We get -3 and then 1/4 to the -5 plus 4 plus 3. We get -3, and then that becomes 1/4 to the -1 plus 3. 1/4 to the -1 is just 4. So we get -3 times -4, which is -12, plus 3, which is -9. We've already calculated that over here. Always good to get practice, though. Okay, plugging in -2. We have -3, 1/4 to the -2 plus 4 plus 3. Okay, from here we have -3, and then we have 1/4 squared plus 3. Okay, let me quit. -3, and then, oops, 1/4 to this square plus 3. We get 2.8125. So I'm going to round that to 3 decimal places, and I get 2.813. All right, the last one that we're going to take a look at is using base E. For this one, we will use the calculator to get the table values because E is Euler's number. And we saw this back when we were talking about exponentials, which was never. So this is the first time you're seeing this. E is what's called Euler's number. You're going to see this name and you're going to want to call it Euler, but it's pronounced Euler. And Euler's number is a constant irrational number like pi. The value of E is approximately 2.718, but it's a non-repeating, non-terminating decimal, so it just goes on forever. We calculate E, or it was discovered, by taking the limit of 1 plus 1 over n to the nth power. And as those numbers n get bigger and bigger, E is the value that it approaches. And it just so happens that this coincidence, I don't know if it's a coincidence, has a lot of applications in real life. And it's a very useful number. So shout out to Euler, shout out to John Bernoulli. They're doing humanity all the favors. Okay. Looking at e to the x plus 5. Here the base is e. Remember, there can be infinite number of parent functions depending on what the base is. So the parent function here is just e to the x. The only transformation we have is it's been shifted up 5. That's going to determine where our horizontal asymptote is at y equals 5. Okay, now, when we fill out our table, I like to plug in, 0, 1, and 2. If I plug in 0, I always get 1. This has become e to the first power, and then this becomes e squared. Applying our transformations, the only thing that's going to change is we're going to add 5 to each of these values. So 0, 1, and 2 stay the same. And we're going to approximate these values using our calculator. So here, y equals, we have, to get the e on your calculator, it'll be the second button, and then ln down here right below log, e to the x plus 5. And then to pull up a table of values, we're going to press second graph. And then if we plug it in, I can see that from 1, it's been shifted up to 6. And then at the value of 1, it's been shifted up 5 to 7.71828. And we're just going to round to 3 decimal places. And then at 2, we have 12.389 approximately. And if it doesn't fit, just let it determine the direction the graph is going. Okay, finding the intercepts. Looking at this graph, you should be able to reason through the fact that there is not going to be an x-intercept. The x-axis is all the way down here, and we're bounded by that horizontal asymptote at y equals 5. So for x-intercepts, none. The y-intercept has already been calculated. It's at 0, 6. Okay, finding the maximum and the minimum, you can see that this function is increasing as x gets bigger. So the minimum should happen at x equals -1. And the max should happen at x equals 3. Okay, plugging these values into our function, we get e cubed plus 5. And then this becomes e to the -1 plus 5. We'll approximate those values. So we have e cubed plus 5. That gives me 25.085. Rounded that up. We get 28.086. Okay, doing e to the -1 plus 5. We get approximately 5.368. The domain of this function is all real numbers, same as all of the other ones. And the range is determined by that horizontal asymptote. All the values on this curve are strictly greater than 5. All right, guys, that's exponential transformations.